Hello, everybody. Welcome to this week's class on betting on uncertain demand, the newsvendor model. Now, in the inventory management stuff that we did before the midterm, we talked about the EOQ model, where we assumed that demand was certain, we knew exactly, or we had a good idea of what demand was going to be. But let's look at a scenario where demand is uncertain. Now, the newsvendor model is one model that you can use when you face uncertain demand. It's absolutely not the only model that you can use, but we'll start with the newsvendor model and we'll talk about other models in subsequent weeks, right? So when is the newsvendor model used? And what is a newsvendor model in the first place? So, as the name suggests, the model comes from the case where you have a person selling newspapers, say at a train station in the morning. Now, what are the decisions that the person has to make? So think of the days when people actually bought newspapers. They would go, let's say they would go to the train station. As they're getting on the train, they'd buy a newspaper and go and read the newspaper. But the newspaper itself was a perishable commodity. At the end of the day, or even by midday, the newspaper would be useless because new news would have come out, and you would have had midday newspapers that came out with more up to date news, and so the viability of the newspaper was only for a very short period. So it's called the selling season. So there is a very specific selling season at the end of which the newspaper is essentially scrap. So what the news vendor can do is either sell it to a recycling center or put it in a trash bin, right? So those are the only options for the news vendor. So they have to decide how many units to buy, right at the beginning. They don't know how many they're going to sell during the day, but they have to decide exactly how many units to buy, and that is a news vendor model. So in a more general sense, the news vendor model considers a setting in which you have only one production or one procurement opportunity, right? There's a single opportunity to procure whatever you can procure or have a production run. Let's say you're printing t-shirts for Super Bowl, right? There's a very short season right after when Super Bowl is done. Once you know who the winning team is, you can probably sell Super Bowl t-shirts for maybe a month, right? And after that, people have moved on to the next season and moved on to what's happening in the camp and who's being traded to which team, and how are the different teams going to draft and so on. So there's a whole different set of decisions that need to be made. So the Super Bowl is not in anybody's mind. So there is a single selling season during which you can sell your item, and it's usually short, right? And the demand during the selling season is not something that we know. So going back to the news vendor might have a decent idea of how many newspapers they can sell, but they don't know exactly what the newspaper is. So demand is considered to be stochastic. That's the word for it. Now, so the opportunity to sell. So once you procure your item, whatever item you're selling, the opportunity occurs well in advance of a single selling season. So you have a single selling season, and this procurement opportunity happens well in advance of the single selling season. So you have to make a decision blind. Now, stochastic demand occurs during the selling season, so you don't know exactly what your demand is. If demand exceeds your order quantity, then you sell your entire order. But if demand is less than your order quantity, then you're left over with something at the end of the season. And you usually have to either scrap it or sell it at a very discounted price. And this is a very common model that is seen in many, many scenarios. We talked about Super Bowl t-shirts, but this is the model that is used for, say, any item that is sold has a particular selling season. For example, you have any fashion good that you take. There's a certain selling season. You might have fall clothes that sell right before fall season, and if they don't sell right before fall season, then they're sent to, say, outlet stores where they're sold during fall season. Or let's say you have red roses. Red roses will sell like gangbusters right before Valentine's Day, as it's coming up, or it could be a couple of other times during the year. But the rest of the time, the demand will be very low. You might have demand for other kinds of flowers, but specifically for red roses, the demand will be slightly low, right? So the news vendor model represents a situation in which a decision maker must make a single bet, a single order quantity, before some random event occurs. And the news vendor model objective is to bet an amount that currently balances the opposing forces. So you do not want the opposing forces of too much or too little, right? And we'll talk about this whole idea of too much and too little as we go through this news vendor model, right? Okay. So how do you implement a news vendor model? To implement a news vendor model, the very first thing that you need to do is generate a demand model. And we'll spend a few minutes on the demand model in the upcoming slides. But the whole idea is we need to at least come up with a distribution that accurately represents what are the possible outcomes for demand. Right now, we will use for most of the calculations, we'll use the normal distribution function, but demand can be any statistical distribution, and the ideas are pretty similar, right? Okay, that's the first step. You generate a demand model. The second step is gather your economic inputs. So things like how much are you going to acquire the items for? How much are you going to sell the items for? Is there any salvage value? So at the end of the day, does a news vendor just have to chuck the newspaper in the bin, or do they have to, or can they sell it to, say, a recycling center and get, say, 10 cents back per newspaper or 5 cents back per newspaper or something like that? So there's a possibility for some salvage. So you need to gather all of these economic inputs and choose an objective. Usually, maximizing profit is the objective that we'll choose. But there's also the idea of satisfying in-stock probability, but maximizing profit is the usual objective that we use. All right. So moving forward, let's talk about this demand model. So demand uncertainty is at the center of the news vendor model. If demand is not uncertain, if you knew exactly how many units you're going to sell over the season, there's no decision to be made. That's exactly how many units you'll order, right? Now, a single order quantity is chosen by the stochastic demand being stochastic. Order quantity could be either too high or too low. And to manage this uncertainty, we have to answer the question, what is the probability that demand will be less than Q, whatever the value of Q? And this is called the distribution function. As you must remember from statistics, you can have different distribution functions depending upon the kind of probability distribution you're looking at. So if you have a random variable, say in this case Q, the order quantity, then it is defined by a distribution function, which we'll say is f of Q, which is the probability of the outcome that the random variable Q, probability that the outcome is lower than or equal to the random variable Q. So f of Q, in this case, for every random variable, let's call it X. Right. So f of Q is the probability that demand of X is a demand which is represented by X, not demand of X, I'm sorry. Demand which is represented by X is less than or equal to this number Q, where Q is how many units you're going to end up ordering. So we are representing the random variable X as the variable for demand. Now sometimes it's easier to call it capital D, so let's call it capital D, right? So there every random variable capital D is defined by its distribution function f of Q, which is the probability that the outcome of this random variable D is less than or equal to this value Q. So if I make a bet and order Q items for the season, what is the probability that my demand is going to be less than those Q items? That's what I need to know. If demand is less than those Q items, then I'll have some items left over. But if demand is more than Q, then I will have nothing left over. I would have sold the entire quantity that I've sold. But even that is an issue. So what is this problem with too much or too little? Let's come back to that in a second, right? So there are two types of distribution functions. You have discrete distributions and you have continuous distributions. So let's quickly talk about discrete distributions. So discrete distributions are functions that can be defined in the form of a table. So you have a set of order quantities, which means that these are the only order quantities you will consider. Now there might be some reason why you only consider these order quantities. In this case, it seems random, but let's say that your order quantities have to come in, say, multiples of 1,000. Why multiples of 1,000? Maybe you can only ship them in pallets, and each pallet has 1,000 units on. Can carry 1,000 units on it, for example. So you only have a set number of possible demands, and then you have the corresponding cumulative probability. So by cumulative probabilities, you mean you're adding up the probability of being less than or equal to that. And that is exactly what a discrete distribution function is. So in a discrete distribution, the random variable takes specific values. So in this case, if this random variable Q can take values 2200 and this should be D. Random variable D can take values 2200 and 3200, and 4200, it means that demand can only be 2200, 3200, or 4200. That's it. Demand cannot be 1000, demand cannot be 2700, it cannot be 2750, right? It cannot be any number other than just these three numbers. Now, a very common type of Poisson distribution, the Poisson distribution is a very common type of discrete distribution function, and that is also used extensively in scenarios like this. Now, we'll come back to Poisson distributions later, or maybe I'll do a different video for Poisson distributions. But right now, let's just talk about the Poisson. Think of Poisson distribution as an example of a discrete distribution, right? Okay. Now, let's look at continuous distributions. Continuous distribution functions, there are unlimited possible number of possible outcomes, which means that you have a range of numbers and your random variable can take any value within that range. Usually exponential distributions and normal distributions are the two continuous distribution functions that are that people usually use. Now, these functions are defined by either one or two parameters. Exponential distribution, for example, has a single parameter, the exponential parameter, while the normal distribution is defined by two parameters, the mean and standard deviation. It's mean and its standard deviation. We'll use mu to represent the mean for standard deviation and sigma. So this is the Greek letter mu and Greek letter sigma. But this is the lowercase version of sigma. I'm sure all of you know that. So this is a lowercase version of sigma. The uppercase version of sigma is what you see when you do summations, for example. Right? So we'll use mu to represent the mean and sigma to represent the standard deviation. It's a common way to represent it. So you'll see me using it throughout this throughout these slides, right? Okay. Now, the question is, what is the optimal order quantity? So if we know that Q is the order quantity, D, the demand D has a distribution function f of Q, how do I figure out exactly what that value of Q is? So it comes back to a similar idea of what we had with the EOQ problem, if you remember. We had two different costs and we found the point where they intersected. We are going to do something similar. But here, this is closer to what you see with, say, if you remember from Econ 101, from when you were in college, for example, if you took a basic economics class, you were looking at what is the optimal value in a market. You look at the marginal cost and you look at so you look at marginal sales, then you look at marginal demand, and you look at the point where the two intersect, and that's the optimal value, and that's exactly what we're going to look at here. Okay, so we are going to calculate the expected loss on the qth unit. So if you have q units, so q is the number of units that we have. What is the expected loss on just the last qth unit? So if I did not have the qth unit, right? If I only had q minus 1 units, for example, then what is my expected loss? And that expected loss is the cost of overstocking. So if you overstock by 1 unit, this is the cost, CO, the cost of overstocking, times the probability that your demand is less than or equal to Q, right? And what is the expected gain on the Q unit? So if you had that 1 extra unit, how much extra money would you make? This is the cost of understocking. So what is the cost of having 1 fewer unit times the probability that demand will actually be more than Q. So if you plot out the expected loss and the expected gain, the point where they intersect is the optimal order quantity. And so if you do some rearranging and blah, 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 you'll find out that the optimal order quantity can be calculated this way. You find the critical ratio. So this ratio here, the cost of understocking divided by the cost of overstocking plus the cost of understocking. So this ratio is called the critical ratio. So you calculate the critical ratio, and then you look at your demand function. So the value of Q, where the demand function is exactly equal to this critical ratio, will give us the the optimal order quantity, right? Now, so this is basically how we calculate the optimal order quantity. In the next video, we will see how you can calculate optimal order quantity and other performance measures when we use, say, the normal distribution. And then I'll post other videos for the exponential the Poisson distribution and exponential distribution and all of that. But let's look at the normal distribution first, and that's what we're going to see in the next video. All right? See you there. Bye-bye.